Hi guys, in this video we will discuss polarity of covalent bonds. Now the original structure bonding outline does provide a brief outline of this discussion. It also introduces a very important topic or term known as inductive effects, which we will refer back to. Very important. But this discussion is largely in the physical properties handout. This handout begins with an overview of the topics to be covered. Please make sure you know what's in the handout. And then some warm-up questions. There's some additional warm-up questions on the backside there. And then we have polarity of covalent bonds. Now we can begin by looking at the hydrogen molecule, HH. This is an example of a nonpolar covalent bond. Nonpolar because the two H's have the same electronegativity. Thus, the two electrons sit in between the two nuclei in a symmetrical manner. And if we sort of drew the electron cloud between the two nuclei, those two electrons are sitting in there very equally shared. A non-covalent polar bond. Now on the other hand, the HCl molecule is an example of a polar covalent bond. Two-electron covalent bond, but the two electrons don't sit symmetrically between the two nuclei. The chlorine is much more electronegative. And you should know your periodic trends. Electronegativity increases as we go up and to the right, with fluorine being the most electronegative element. So if we draw the electron cloud, it's going to look more like sort of this, with those two electrons sitting closer to the chlorine nucleus, leaving the hydrogen nucleus, sort of the electron, the valence electron of hydrogen has sort of been pulled away. And this is actually going to leave behind, if you pull electrons away from an area, this is going to make the area more positive. And as the electrons move more towards the chlorine becomes more negative. Now these are not formal charges. These are partial charges that result from polarity. These are also known as dipole moments. And you can actually calculate the amount of partial charge on each atom, either negative or positive. But we're not going to do that. A very generic description here is to draw a dipole arrow with a positive on one. It's an arrow which showing how the electrons are moved. They're moved in this direction to the right, leaving, and we'd show a little plus sign on the other end of the arrow. Now we can also indicate this by showing partial minus and partial positive charge. I'll draw those again. A partial sign minus and partial plus. Either way, typically you do not draw both, one or the other. So Chlorine is much more electronegative than hydrogen, leading to a molecular dipole moment here, a polar molecule. Now, this molecule is only one bond. Down below, we'll judge polarity of molecules that have more than one bond. Other examples of polar bonds, well, the carbonyl is a common example. Of course, it's a carbon double bond oxygen, but the oxygen is more electronegative than the carbon, thus it's pulling electrons towards the oxygen, and the oxygen is partial minus, and the carbon is partial plus. The electrons pulled away from the carbon, and that's shown over here with the partial plus minus. We see carbonyls a good bit in compounds, and so it's important to know the polarity of the carbonyl. Many other examples possible. You need to know your electronegativity trends. This interhalogen molecule, the chlorine is more electronegative than the iodine. The chlorine pulls, leaving the iodine as partial positive and the chlorine as partial negative. What about for the BrCl molecule?
No.
Well, chlorine is more electronegative than bromine, so we have the same dipole. The bromine is partial positive, the chlorine is partial negative. Let me ask, of these two halogens in the BrCl molecule, which one is more electrophilic? Well, the iodine and the bromine are electrophilic. Electrophilic equals electron poor. Things that are electron poor will like to have electrons. They're electron poor because the chlorine is electronegative and it has pulled the electron density away from the iodine or bromine. H2O. We have two bonds. Oxygen is much more electronegative than H. Any of your heteroatoms, oxygen, nitrogen, sulfur, halogen, are going to be more electronegative than H. Pulls on the H, leaving the H partial positive, and the central oxygen partial negative. Now we'll have to judge the overall molecular dipole moment, but first we need to get the bond angles right, and I'm not so sure that this is a linear molecule. We'll come back to that. Another example, carbon bonded to bromine here. Your halogens are more electronegative than carbon. Bromine is partial minus, carbon is partial plus. And the carbon is electrophilic. Thus electrophilic. That will be important when we get to substitution reactions, which this molecule can undergo. Understanding while a nucleophile will attack this carbon, it will attack it because it's electrophilic, it has some partial positive charge, it is electron poor. So terminology, electrophiles, electrophilic. We can also bring in the term that was listed on the outline. Inductive effects. Withdrawing or donation of electrons through single bonds. You can read the rest of that. That's what's happening here. Through the single bond, the bromine is pulling on the carbon. It's through an inductive effect that the bromine is making the carbon electrophilic. Now, in some cases, we will talk about donation as the definition indicated. Withdrawing or donation. This is an example of the bromine withdrawing inductively. Okay, let's sort of expand upon this idea of, which by the way, you should have hopefully seen some in Gen Chem. Okay, here's some molecules. Polar or not, H2O. Again, we have to understand that the oxygen is, well, there's two lone pairs. And that oxygen is sp3. It's tetrahedral. And if we draw tetrahedral, we can put one in the plane. I'm sorry, two in the plane. And then we can put one forward and one back. And these can be the lone pairs occupying those regions. But essentially that leads to this bond angle here being 109.5. Or approximate. In Gen Chem you probably learned that this bond angle is smaller than 109.5 because the lone pairs sort of push as they kind of demand more room. But for me, typically tetrahedral, we're always going to say 109.5, which is the standard bond angle. But we see that the HOH is not linear as drawn above. Because of that, the individual dipoles do not cancel each other. They are equal. Now this is vector addition. Perhaps you've done some vector addition in a math course or a physics course. And for these two vectors, dipole has a vector. For these to cancel, they need to be equal and opposite. These two OH dipoles are equal, but they're not opposite. They would be if it was linear up here. These two vectors sum up to make one vector, or one dipole direction, molecular dipole direction, in this so molecular dipole. So this area over here between the H's is partial positive, and this area over here between the lone pair regions is partial negative. That kind of makes sense. Lone pairs are negative. The region over here would be negative. So this is a polar molecule because it has a net molecular dipole that comes from vector summation of the individual dipoles. Yes, water is a polar molecule. What about CO2? Well, we need a Lewis structure. How many valence electrons in CO2? 4, 6, and 6, 12, 16. 16 valence electrons. Carbon typically in the middle, bonded to each oxygen. Fill the valences of oxygen. Two, 4, 6, 8, 10, 12, 14, 16 valence electrons. Carbon doesn't have an octet. Let's ask the oxygen to share. This is actually going to be a resonance structure, which, by the way, we may not have clarified in a previous video. What does arrow mean? One lone pair is moving in to make what? A second bond. We're not moving this lone pair to this carbon. This arrow means it's moving in to make bond. We will never take a lone pair and just magically put it and move it over to the carbon. This leaves behind 2 lone pairs. I want to put charge here. We didn't put any charge over here, but this oxygen is minus. The carbon is plus. If you want to do charges over here, this is 2 minus, 2 minus, 2 plus. You should be able to determine formal charge. Carbon still needs another bond so we can get it in an octet. We could move this one in. Instead, let's move this one in because it has more electron density, and that leads to this mechanism arrow leads to this bond here, 2 lone pairs left. Now this carbon in the middle has an octet, 2, 4, 6, 8 electrons around it. 4 bonds, no lone pairs. Standard bonding. Resonance. Anytime we just move electrons and then show another structure, we're typically doing resonance. We didn't move any atoms when we went from here to here or here. Just moving electrons. And more specifically, we moved pi electrons. Because if you think about it, this lone pair is in a p orbital, that lone pair is in a p orbital. Why? Because there's p orbitals on the neighboring carbon. So if you do hybridization of this structure, you will see the p orbitals. They're of course still there. This is typically the structure of carbon dioxide. Hybridization for the central carbon. 2 regions, we expect sp and linear. Indeed, it is shown linear. We have dipole. Oxygen is pulling. And oxygen is pulling. Those 2 dipoles are equal. Both involve C and O. They are also exactly opposite because of the linear arrangement of the 2 CO bonds or double bonds. Equal and opposite dipoles cancel. Nonpolar. All right. The individual dipoles cancel. Now, what are the consequences of nonpolar? We want to understand. Okay, we don't want to just be students. We want to be real people. We want to be scientists. Well, what is this information useful? How's it used, applied? What does it mean to be polar? What does it mean to be nonpolar? When you talk about solubility, we talk about like dissolves like. And so a nonpolar molecule, now CO2 is usually a gas. It can be liquefied and be used as a solvent. A nonpolar solvent is going to be better at dissolving nonpolar molecules. Nonpolar, well, let's look at this. What if we put this compound in an electric field? And we had partial minus, partial minus, partial plus. And we had, I believe physics would serve me right, if we had some electric field and we had partial positive here, we had partial minus here, question I could ask you, would this compound experience a torque? Would it turn? Would it rotate? You might think that the partial minus would want to move up this way. That's not a mechanism error, that's just a possible movement. Well, guess what? This end would also want to move up this way. All right? And if forces are on each end, I mean, which one's going to move up? Well, neither will. And so there is not an immediate torque that's evident here. So maybe in your physics classes you will look at some of the consequences of polarity here for the molecule. CO2. What about SO2? We need a structure. SO2 would be 18 valence electrons. Typically, the less electronegative atom in the center. Is that right from Gen Chem? I just know that SO2 is going to be S. All right, oxygen. Now, I kind of know something already, so I'm going to go ahead and draw this like this. Now let's fill the valences of the more electronegative atom first. Oxygen is now good. How many electrons? 2, 4, 6, 8, 10, 12, 14, 16. Only 16. We need to put one more lone pair. And it goes on the sulfur. And that's the reason I made this bent, because I wanted to have ultimately a trigonal planar. 3 regions around the sulfur. Now at this point, that oxygen's minus, that oxygen is minus, and the sulfur is 2 plus. Let's ask one of these oxygens to share. And let's get a resonance structure that looks like this here. Now the sulfur is positive, that oxygen is negative, the other oxygen is neutral. Now the sulfur has an octet, 2, 4, 6, 8. Now you can draw another resonance structure here. We can move these in, and that would give sulfur double bonded to both oxygens. One lone pair still. The reason you can do this is because, remember, sulfur has d orbitals and we can go beyond 8 electrons, 2, 4, 6, 8, 10, expanded octet. Some folks will show SO2 like this, some will show it like this. The rationale for showing it like this is you have no charge. All atoms are neutral. No charge separation. The big difference between SO2 and CO2, CO2 is linear, but the SO2 has a bond angle. It's not linear. Dipole. Oxygen is more electronegative than sulfur. Those two individual dipoles are equal, but they're not opposite. This has one molecular dipole sort of right up between the two oxygens. This area over here, partial positive. A little bit counterintuitive. This area over here contains a lone pair of electrons. How is that partial positive? Well, it may not be a great, it may not be a large dipole, but this is theoretically the direction of the molecular dipole moment. Largely governed by the oxygens being more electronegative than the sulfur. So SO2 is actually a polar molecule where CO2 was nonpolar. Okay, next here is some of the one carbon with either 4, 3, or 2 chlorines, halogens. I'll actually let you work on these yourself and determine if they are polar or nonpolar. Now these three are actually solvents. That's one carbon would be methane, CH4. If you start putting one chlor would be chloromethane, 2 chlorines would be dichloromethane. This would be called trichloromethane, but it actually goes by a common name of chloroform. Chloroform actually has some historical significance. It used to be used as an anesthetic. Queen Victoria actually took some chloroform during childbirth to relieve some of the pain. And this could be called tetrachloromethane, but instead it goes by the name of carbon tetrachloride. That's a more common name, or sometimes abbreviated as carbon tet for tetrachloride. But these are all three solvents. Today, dichloromethane is still fairly common, chloroform a little bit less common. Carbon tetrachloride is not used much anymore, largely it's because of its toxicity. And also halogenated solvents are sort of been phased out a good bit due to ozone depleting considerations. But we will use dichloromethane in the lab. So is it a polar or nonpolar solvent? Try these on your own. Now the extreme polarity is ionics. If we consider something like sodium chloride, which is not covalent, but if it was, there's such a huge difference between the chlorine and the sodium. Far right periodic table, far left. Huge. But it's actually such a difference that that chlorine just takes these electrons and strips them away. Just pulls them away. And so when this molecule, when these two atoms bond together, the chlorine is so greedy, it just rips the electron away from the sodium, and it's no longer covalent. It's actually a pair of ions, an ion pair. And we call this an ionic bond. And this is sort of the extreme of polarity. But I caution you, I actually would not call it an ionic bond. And in Gen Chem, I would have said, let's call this an ionic attraction. Because I want to keep you out of trouble. And if you don't call it a bond, you'll stay out of trouble a little bit better. So we have an ionic attraction between the sodium ion and the chloride ion. And this is actually a mechanism arrow, as if the two electrons were just pulled away and move on to the chlorine to become the fourth lone pair. Now, of course, this molecule never was like this. Okay, let's take a look at physical properties of various functional groups of molecules, organic molecules. And we will look at boiling point / melting point, and then we'll also look at solubility. But the solubility portion of this handout has been covered in a separate video. Now it's important to understand that for a compound to boil or to vaporize, the compound must first overcome all intermolecular attractions or intermolecular forces, which we call IMFs. Those IMFs must be broken for the molecule to move into the gaseous state and to go from liquid to gas. Now in general, the more intermolecular attraction, okay, more IMF. Here, attraction of forces, same thing, intermolecular forces. The more of that you have, the higher the boiling point will be. We can consider the IMFs to be stickiness, and the more sticky the molecules are to each other, the more work and energy you're going to have to put in to break those molecules apart from each other. And the more energy you're putting in, that means more heat. And so we're saying it takes more heat to break apart the molecules and get them to go into the gaseous state. More heat thus equates to higher boiling point. So, if we're talking about IMFs, we've got to know what are the different types of IMFs that are possible. And these are the 4 that are possible. And we will discuss each of these in order. And the first one will be the van der Waals attractions. Now these 4 are also listed in order of polarity. Van der Waals is the weakest of the polarity. And ionic attractions is strongest polarity. Now, van der Waals attractions are sometimes called other names. There are kind of minor differences in them. You may have heard of London forces or dispersion forces. I consider them pretty much all the same, and I will simply call them van der Waals attractions. So, number 1. Here's an example of van der Waals attractions and how that can influence boiling points. Here are 3 hydrocarbons. Propane, boiling point of -4 degrees. It's actually a gas at room temperature. Pentane, on the other hand, has a higher boiling point. It's actually a liquid at room temperature, with room temperature being about 22 degrees Celsius. And so we can ask, why does pentane have a higher boiling point than propane? Well, the answer is it has more van der Waals attractions. Now, van der Waals attractions are very weak, okay? Weak polarity. And it comes from temporary dipoles. Temporary dipoles that are induced by molecular contact. And this illustrates 2 molecules of propane coming into contact with each other. And we have to keep in mind what's on the sort of the outside of the molecule, sort of like the exoskeleton. Well, that's the electrons. Because sort of buried inside is the nuclei, with the electrons out more on the outside. So the electrons come into contact with each other. And what we can show here is basically an electron cloud around the molecule. And we see a larger electron cloud around this molecule, largely because it is a larger molecule. This molecule has more surface area. And more surface area equals more van der Waals attractions. And because you have more van der Waals attractions between the molecules, you have more stickiness and thus a higher boiling point. Now, the temporary induced is, as these electrons sort of come in contact with each other, they're sort of perturbed. They start moving around. Okay, we can come in and this one kind of moves, and this creates very fleeting, temporary, weak dipoles. But it's strong enough to have an effect. And the take-home is, the more surface area you have, the more the electrons are bumping into each other between two different molecules. More surface area, higher boiling point. And so when you look at these two, we say, hey, larger molecule, more surface area, higher boiling point. But take a look at this alkane, a branched alkane. It's got the same formula. These two are constitutional isomers. But this one has a lower boiling point. Do we expect that? And the answer is yes, because this one, if we look at the surface area, the surface area is not as great as with the straight chain hydrocarbon. See, this one, because of the branching, we've got this carbon sort of hidden in the middle, and it can't contribute as much to the surface area. So the take-home here is branching lowers the van der Waals. It lowers the surface area, it lowers the van der Waals, and thus branching is going to lower the boiling point. So you look at these two isomers, you would expect the branched one to have the lower boiling point because it has less surface area. Okay. Next, let's look at dipole-dipole attractions. Number 2. It's going to be a slightly more polar type of IMF. Slightly more stickiness. 3 examples: a hydrocarbon, boiling point 36. This ketone, the boiling point is a bit higher, 76. And then this alkyl chloride, also a bit higher than the alkane at 78. Why are these two higher? Well, because they have permanent dipoles. These two compounds are both polar. Now, if we go back over here, all right, this molecule only has one dipole. There's nothing that can cancel it. Your carbon-carbon, there's no dipole. CH, there's no dipole. Nothing to cancel that dipole, nothing to cancel this dipole, and so they're net polar molecules. But this molecule here is nonpolar. Now these are permanent dipoles. This only has fleeting temporary dipoles we call van der Waals. Weak. Permanent dipoles are stronger. And we can show the IMF network here. The permanent partial minus of the oxygen can coordinate to the partial positive of another molecule. And we show this with sort of the dashed here. It's a non-covalent interaction. That we're showing here with the dash. sort of like a partial bond. Not a true covalent bond, but some type of non-covalent interaction. But see, each of these molecules can be sort of stuck together like this because of the permanent dipole. And such is possible for both of these compounds. I mean, over here we could draw the chlorine is partial negative, the carbon is partial plus, and we could draw a non-covalent interaction between the chlorine and the carbon. Between the chlorine and the carbon. And we can sort of start sticking all these molecules together by IMFs, non-covalent interactions. But because it's permanent, these partial positive and negatives are stronger than you get up here with the temporary, fleeting, induced dipoles, much weaker. And so the stickiness is weaker up here. Next, hydrogen bonding. Now, hydrogen bonding is actually just a specific type of dipole-dipole, but it's particularly strong. It's stronger. It gets its own name. And let's look at these two examples. We have an alcohol and an alkyl chloride. And the alcohol has a significantly higher boiling point than the alkyl chloride. Why? Well, hydrogen bonding. Now, hydrogen bonding is a particularly strong dipole-dipole interaction that occurs between oxygen, nitrogen, or fluorine. And in particular, especially the lone pair of the oxygen, nitrogen, or fluorine. Okay? And that lone pair on these atoms is called the H-bond acceptor. These three, largely because these are the most electronegative atoms that we'll be working with on the periodic table. Now, these lone pairs will form a hydrogen bond to a hydrogen that is on an O inner F. And the H that is on one of these atoms is called the H-bond donor. And here we show the hydrogen bonding network that is possible for the alcohol. So here the lone pair on the oxygen is acting as an acceptor, and the H that's on the oxygen is acting as the donor, and there is a non-covalent interaction between the two, the so-called hydrogen bond. And this is very similar to what we showed over here with the alkyl chloride. The difference is it's much stronger in this case, but it's much stronger when it involves an O inner F and an H on an O inner F. And it also is thus called a hydrogen bond, where over here we would not call this a hydrogen bond. Of course, there's no H even involved. It's chlorine and carbon. but this is weaker. It is dipole-dipole. And this is dipole-dipole, but it's stronger. O-N or F. Because it's stronger, there's more stickiness between the molecules of the alcohol, and it requires more heat to break the stickiness, to break the IMFs, and thus it has a higher boiling point than the alkyl chloride, as expected. Question. Look at this ether compound here. Can it H bond to itself? And the answer would be no, it cannot. To H bond, you have to have an acceptor and a donor. If you only had this ether, you would only have acceptors, oxygen lone pair. Where's the donor? There is no H on an oxygen inner F within this molecule. But can this ether hydrogen bond to water? And the answer is yes. Because if we showed it, we could have right here, I won't show dipoles, but the oxygen lone pair, hydrogen bonding to the H of water. Now, of course, the alkyl chloride cannot H bond to itself. Again, well, it has neither an acceptor or donor. It's no hydrogen bonding possible at all. And it could not hydrogen bond to water. Question. How many H-bond acceptors and donors are present in the antidepressant drug known as Effexor? I have an oxygen, I have a nitrogen, I have oxygen. Acceptors. I would say 3 acceptor atoms. Might want to clarify that, acceptor atoms. The question becomes, is each lone pair individually an acceptor? Theoretically, I'd probably say yes. 1, 2, 3, 5 acceptor lone pairs. Depends on how the question is asked. What about donors? Well, there's just one, right? A donor is an H on an O inner F. We only have one H that is on an O inner F. Could this drug molecule hydrogen bond to itself? Yes, the nitrogen of another molecule could hydrogen bond to the H of the alcohol. And possibly there is other types of hydrogen bonding you could show. It's also possible to have an internal hydrogen bond. Maybe this nitrogen could hydrogen bond to the H that's internal. 1, 2, 3, 4, be a 6-membered ring there. Yeah, probably it's an intramolecular hydrogen bond, where the one I showed here was intermolecular. Some other examples of how hydrogen bonding can greatly influence boiling points. These two are constitutional isomers, same formula. The alcohol has a much higher boiling point than the ether. It's actually a gas at room temperature. And the alcohol is a liquid. Why? Well, the alcohol can hydrogen bond to itself. The ether cannot. These two amines, constitutional isomers, the primary amine can hydrogen bond to itself. The tertiary amine cannot. Water, boiling point 100. H2S, much decreased boiling point. 160 degrees lower. Water can hydrogen bond to itself. H2S cannot. Yes, H2S has dipole-dipole, but that is much weaker than what you get when you have these atoms involved. A much stronger dipole-dipole interaction that we call hydrogen bonding, and we see the difference. Much more stickiness between the water molecules. Now, change that to carbon and put two more H's on it. Methane, the boiling point goes even lower. This one has hydrogen bonding. This one has dipole-dipole, because that is a polar molecule. This one has nothing but van der Waals. But also, it's a very small molecule with small surface area. Not much stickiness holding these molecules together. Very low boiling point. One last example, antifreeze, 2 carbons and 2 oxygens versus butane, 4 carbons. Very similar molecular weight, but antifreeze has lots of hydrogen bonding possible. Lots of IMFs. Lots of stickiness, increasing the boiling point by about 200 degrees versus butane. Now, hydrogen bonding is seen many other places. For example, what holds our DNA together in a double helix? Hydrogen bonding. And we also know that the AT bases like to pair together because, let's put in lone pairs here. When they come together, there's 2 hydrogen bonds that are possible, as shown here with the non-covalent interaction. And the GC, when they come together, you have 3 hydrogen bonds that are possible. And these bases selectively coming together, either AT or GC, is what leads to, and some other things. There's twisting that comes for other reasons. But that's what holds the 2 different helices together to make the double helix structure. Now the fourth was the ionic attraction. And ionic attraction is the IMFs that are between ions, and this is your strongest IMF. If we look at sodium chloride, salt has a boiling point of 1400 degrees. I'm not sure how this was determined. Probably under vacuum. If you can imagine table salt boiling. But these are formal ions, and this is going to be very strong attraction. Now that's just between 2 ions, but consider you have lots of ions in the unit cell, and they are all of these ions are associated to each other by non-covalent interactions. And so you got millions and billions of ions all stuck together by strong IMFs because of the formal charge, real formal charge. I can show you an example here. A regular alcohol, boiling point is 78. If we can make this ionic by removing the proton in an acid-base reaction or some type of other mechanism and make the oxygen minus and have a counter ion with it, this molecule, ionic molecule, is expected to have a much higher boiling point, and indeed it does, now 500 degrees. And the alcohol is a liquid at room temperature, while the sodium salt is a solid. Very high IMFs here. When we go from gas to liquid, the IMFs gets stronger and taking more effect. If those IMFs become even more stronger, we are more likely to become a solid. And so this is a solid, and of course sodium chloride. Most ionics are solids because the IMFs between all the ions are so strong. Okay, let's work towards finishing up this video by looking at melting point. Melting point is going to be the similar arguments throughout, except here we're going from solid to liquid as the compound melts. And to melt the solid, we have to break some of those IMFs a little bit so the molecules can start moving around. In the solid form, the IMFs are strong and the molecules are rigidly held together. With heat, we start maybe breaking some of those IMFs just a little bit. Instead of strong, it breaks a little bit, and now the molecules can start moving around. Weaker IMFs, and if we break these IMFs, then the molecules can move off into the gaseous state. Two amides here. One has a melting point of 126, 144. Which one has the higher melting point? Well, there you go. The question really is, which one has more IMFs? Possible. Not possible. Two molecules of this primary amide can H bond together. We could show maybe the... Okay, I'll just show one NH bond. It can be hydrogen bonding to the oxygen. But you cannot do that with this amide. We have an acceptor, but there's no donor. More stickiness leads to more IMFs, leads to higher melting point. Now, this molecule can hydrogen bond to maybe ethanol. But it can't hydrogen bond to itself. And a solid is going to have a sort of a crystal structure of repeating molecules over and over. And this crystal structure, the IMFs are going to be weaker than this crystal structure. Okay, we covered a good bit there. Different IMFs that are very important. Some applications. We'll see what type of questions came up. And in the next video, I look at the remainder of this handout, which largely focuses on solubility. Now, in that discussion, we will consider the same types of IMFs, including our good buddy hydrogen bonding, very important. Okay, guys, that finishes up this video.